Okay. Again, this is going to be my little experiment today. I'm going to see how well this can handle this. I have no idea about the low light situation or... actually, I'm going to leave the lights on for right now. And no, not. We're coming to it. Alright, here we go. Alright, first. Let's talk about what we're going into. On Friday, if you were gone, we did the logic grid problems where we talked about the Olympic problem where they had to figure out their sleds, their partners. So if you did not watch that video or if you did not have that grid, you should be filling it out. That is worth 20 some points, so you might want to get that turned in. So those will be in probably tonight. And then I'll hand back those things pretty soon. We're looking at probably a test in chapter 2 for us because we're kind of wrapping up. I think there's only 5 sections or something. We're probably looking at a test probably middle of next week. And I won't push it past next week because the week after that is I think the last week of the quarter. So we have like 3 weeks, right? This week, next week, and then the next week after that. So I think we have a test middle of next week. That way it gives you enough time if you want to take a retake. I don't like to push it near the end of the quarter, then you can't do anything about it. So keep that in mind. If you're one that were like, you're dying to take a retake on that last chapter 1 test, you need to get that done. Like, I have extended that so far, you probably don't even remember what's on it anymore. Because there's some people like, I don't know why, I have to tell them explicitly, like, hey, you have to retake it. Okay, conditional statements. Here's our goal today. We need to talk about the if-then statements. Give you a couple examples of this. Talk about compound statements where we have disjunctions and conjunctions today. That was a part of that logic grid. But today we need to actually apply it to like kind of the more math concept type of problems. And what we're going to look at today is, can you identify what a hypothesis and conclusion is on a sentence? Can we figure out counterexamples, all that good stuff? So let's do an if-then statement. I'll do kind of an if-then math statement. So if x squared equals 16, then x equals 4. I like to write that sentence down. That's an if-then statement. It's including math. Some people say that type of thing in their head. They try to justify answers on tests or homework like, oh, what I just did in my head. You did it wrong in your head. Because you're supposed to show work, you're supposed to show why your answer is 4, that type of thing. So this is our first if-then part. Now, when you look at that sentence, there's 2 parts. There's a hypothesis and there's a conclusion. What do we remember from last week? Which part is the hypothesis?
The if.
The if part. So on your homework that we're going to be eventually getting this week sometime, this is the hypothesis. I'm not joking. Like that first assignment you're going to have this week is going to ask you to underline the hypothesis and label it. And then we have to underline the conclusion. Well, what's the conclusion then?
X equals 4.
X equals 4. That's the conclusion. I know that's super simple, super easy to figure out, but the problem is they're going to have the sentence in different formats. So they'll use if, implies, they'll say only if, that type of thing. You got to know which one's which. We're going to look at that more tomorrow, but today was just to understand the 2 parts. Questions on which part's the hypothesis, which part's the conclusion. Now, here's my real question. Is that true?
Yes.
Okay. What if I told you it's not? Now what? Because what they're saying is that your only answer is 4. There's another answer that would have worked. And I know that seems really weird. Like, you're thinking, word, 4 squared is 16. Yeah, but it's not the only answer.
-4?
-4. They had to include both. So there is an actual counterexample to this. There's an actual counterexample, which is a new term. We're going to look at that here in a second. You have to kind of be thinking about, is there another option? Because what they're saying in this sentence is that this is your hypothesis. The hypothesis has to be true. When you square a number, it gives you 16. That has to be true. But the problem is, it's this part. They're saying that the only answer is 4. It's not. It could have been -4. So your counterexample is x could equal -4. That's a counterexample because it follows, this was a check. This number you're squaring has to be 16. but you're disproving their conclusion. Their conclusion was wrong, that it could have been positive 4 only. It could have been negative. So you have to be kind of thinking about counterexamples today, that there could be another option. We're going to try more of these. We're going to try more math-related stuff today as I go through examples, to get you kind of open up your mind to think about, okay, is there another option, or is that the only one? Because if it was the only one, you'd say true. This is actually a false statement. There's actually 2 answers. I probably should have both. Okay, questions at all about hypothesis and conclusions? Perfect, let's move on to the next slide. So we'll get to the actual other vocab here. We're going to come back to this throughout the day. I'm going to try different examples for you so you can kind of see how they work. Okay, so the different types of conditionals I want you to be comfortable with. Number 1, counterexample like I just showed you. Is there a counterexample of that problem? So, for instance, if a quadrilateral is a rectangle, then it is a square. That's a math statement. Do you agree that's an if-then statement? Okay, what's the hypothesis on that problem? What's the hypothesis?
A quadrilateral is a rectangle.
Yeah, quadrilateral is a rectangle. That's your hypothesis. That's the if part. You have a 4-sided figure, it has to be a rectangle. Their conclusion, it has to also be a square. Is that true or false? If your shape is a rectangle, then it also has to be a square. It is false. Whoever said that. It is false. Why?
Because a square is even on all sides of a rectangle, isn't it?
Yeah, your counterexample, perfect example, a counterexample to this. What if your picture looked like this? Do you agree that this picture is a rectangle? Okay, it is, right? It's got 4 walls, it's got right angles. That's the definition of a rectangle, by the way. It had to be a quad, it has to be a rectangle, it has to have 4 right angles. So I made that picture. Is my picture a square? No. I showed a perfect counterexample. It followed the first part, check, that the hypothesis was true. It's a quad, has right angles. That's a rectangle. Their conclusion that it had to be a square is false because my picture follows the hypothesis but disproves their conclusion. And it's exactly what Bree said. It doesn't have to have 4 equal walls. That's not the definition of a rectangle. Sure, there could be that one special case. That could be, but if you could think of other cases, then you have a counterexample to it. So, does this make sense that this is their counterexample to that problem? Like you can think of a different picture. I mean, counterexamples can be pictures. Like you can show a picture that follows the hypothesis. So I want you to kind of think outside a little bit when you're actually coming up with some of these, because they're going to ask you, a counterexample of this problem. You just have to think about it. Okay? Alright, so that's counterexamples. We'll do more later. So, next. Converses. This is something that we haven't had before. A converse is when you take a conditional statement, an if-then statement, and you switch it around. You take the sentence and you literally write it backwards. Okay? So, for instance, I'm going to go back to the first statement that I said earlier. So, if x squared equals 16, then x equals 4. Right? We already said this is false. There was a counterexample to it that you couldn't be negative for. Fine. Do you agree that it's still a conditional statement? It has an if-then part in it? You can take any if-then statement and you could turn it around. So, you could change this to what they call a converse. This is the converse to this sentence. A converse is where you go if and then stay where they're at. They stay. But what switches is the 2 parts that were the hypothesis and conclusion. So if x equals 4, then x squared equals 16. Converse, you just switch the hypothesis conclusion, but the word if and then stay where they're at. So you're switching their parts now. So now the new hypothesis is x equals 4. The new conclusion is when you square it, you get 16. Now, here's the crazy thing. When you do a converse, it could turn out to be true or false, and it could be different than the original problem. Like we already said, the original problem was false. Like there was another counterexample to that problem. In theory, there was another one, so we had a counterexample. When you do a converse, it's a totally new sentence. You have to rethink it now. So you have to really start over and see, okay, is this new sentence true or false? That if they gave you the number 4, and they were to square both sides, so like x squared, and you square the other side, will you get 16 if you square both sides? This is actually a true statement. Because they're saying if this is actually your number, and you were to square both sides, would this actually turn out to be the right problem? Yes, it would. It's not saying that's the only thing, it's saying that if you were to square both, that is true. The reason why this is a true statement, it's literally a property of mathematics. So you have to think about, okay, if you know all the properties of like algebra 1, properties of equality, name one, this is actually true. It has to be true for that thing to work. If you were to square both sides, you get x squared equals 4 if you square both. So the converses could be true, or they could be false. It could be completely independent of the first sentence. Sometimes they're both true. That could happen. They could both be false. But do we feel comfortable with what a converse is in the first place? You can switch it. Okay. It's sometimes nice to think about a problem backwards. Usually a really good property in mathematics, like a really, really good property, is one that if you write it both ways, it's still true. So if you write the original conditional and you were to flip it around and write the converse and that they're both true, it's probably a property in mathematics, usually. Like this is a rare case. I should have had plus or minus and then it would have been like all the way true, for sure. All right, that's a converse. Now the other type of term that we need to know is called an inverse. This is something completely different now. An inverse is where we're going to throw in a new term now. Is where they're going to negate your problem. So this is something that we need to talk about. It's part of a negation. Negation is when you change the sentence to mean the opposite meaning. So if I said, if it's raining outside, then it's sunny. A negation of that could be if it's raining outside, then it's not sunny. It's like the complete opposite meaning of what the sentence meant. You throw the word not in there, okay? But an inverse is where you're actually negating the original sentence, but you're negating both parts of it. So let me go to that first sentence. What did I write earlier? It was if x squared equals 16, then x equals 4, right? That was the original sentence, correct? Is that what I had? Okay. And an inverse to this sentence, an inverse, is where you literally make both the hypothesis and conclusion an opposite. So, if x squared does not equal 16, then x cannot be 4. That's an inverse. It's the original sentence, but you throw the word not in both parts. It's the complete opposite meaning. Does that make sense? Now, an inverse has its own truth value, a validity to it. So you have to look at that. Okay, so they're saying if you're to square a number, it can and it doesn't turn out to be 16, then the number can't be 4. That's true. The number can't be 4 if you square it and it doesn't equal 16. Okay. Now they're saying that that's the only number it can't be. It could be -4 as well. So this one would actually have a counterexample. Your answer couldn't be -4 as well. So even though we did an inverse, you can still think of it. You can still think of counterexamples. This one can be negative or positive 4. So that's a counterexample. Because this has to be true. When you square a number, it can't be 16. So you got to think about what are the two options I have. 4 and -4. Those are the two options I have to throw out. So their conclusion would be wrong. There's another number. Do we understand what an inverse is, though? Okay, they're all independent sentences. Yes? Yes. All right, let's go to the next word. Next word now. Contrapositive. All right, contrapositive is based on the converse. So this is going to take a little bit here. I'm going to go back to that one that I did with the. I'm going to go back to the one with the rectangle and square. Let's go to that one because I've been using that one too much. So the original conditional statement. The original conditional is if a quadrilateral is a rectangle, then it's a square. Now we already said this is false, like it didn't have to be. I think we can look at a great counterexample. Okay. The converse is where you flip it around, so let's go to the converse. I know we're trying to get to the contrapositives here, but we have to look at the converse first. The converse is you switch the two parts around, so if a quadrilateral is a square, then it is a rectangle. So that's doing a converse, you switch this sentence around. But a contrapositive is where you put the word not in there on the converse. So it's negating the converse. So, contrapositive. Contrapositive. If a quadrilateral is not a square, then it is not a rectangle. Make sense how you throw the word not in there now? I always remember the pairings. Converse, contrapositive. They're paired together, they both have the word con in front of them. So that's how I remember that those two are paired together, converse and contrapositive. Inverse goes with original conditional statement. So just to kind of clarify, this is the negation of the original sentence, and the contrapositive is a negation of the converse. That's how I think of it. Negation is where you throw the word not in there, and you make the sentence completely the opposite meaning. They could have their own definition. Like, for instance, if we went to the sentence, we already said false, like Bree did a really nice example of why this is not true. The converse is true. If a quad is a rectangle, or if a quad is a square, then it's also a rectangle. That's true. A square is a rectangle by definition. So it's that subcategory. So if you know your picture is a square, it's also classified as a rectangle by definition. It's four-sided, has right angles in it. But the contrapositive might be false. Even though the converse is true, the contrapositive might be false. The quad is not a square, so you got to think of any picture that's not a square, then it's not a rectangle, it's false. It could have been a rectangle, it just wasn't a square. So that's a false statement. So even though you had a converse, the contrapositive could be the complete opposite meaning. So you got to be thinking about that. Okay, do we understand the three parts? Okay, we're going to practice these more. Don't feel like I'm going to just turn you loose on homework. I'm not going to do that to you. We have to go through a lot more tomorrow. I'll try to come up with a bunch of different examples for you to look at tomorrow so we can get some practice where we write sentences down. So when you come in here tomorrow, we're going to do a lot of different things. So today is the intro of the words, so you can see them for the first time. Some of you have never seen these words. Okay, we good so far? All right, next. Negations, make sure that you understand that's putting the word not in there, or if they have an equal sign, just putting a slash there, it means not equal. We need to know what a negation is when you get to the inverse and contrapositives. We totally negate the original sentences that they're based on. So we're going to look at that. We're going to look at the symbol here in a second of what a negation actually looks like and how you can apply it to like other math statements. So we're going to try to practice that. Hopefully you feel comfortable with that. And the last thing is, I haven't done any sentences today where we did a bunch of biconditionals, like if and only ifs. Remember, we're gonna look at that tomorrow, like where we look at all the different forms of how you can write sentences down, and they still mean the kind of the same thing. So, this is gonna be our goal tomorrow. Then we're gonna try to apply with negations and stuff. All right, related conditionals. Converse, I just went over an example of that. If you're exchanging that hypothesis conclusion, make sure that that makes sense to you. Example of the converse, it's where I said, you had a quad is a rectangle, then it's a square, and you flipped it around, you said a quad's a square, then it's a rectangle. That's converse by definition. The inverse is where you negate the original statement on the original conditional. So you negate both hypothesis and conclusion. So the example I gave you earlier was if x squared equals 16, then x equals 4. But you just put the word not in there, you make them both slash. They're not equal. That's an inverse. It negates the original sentence, both parts. And then the contrapositive is where you negate the converse. So the reason I threw this slide in there is in case if you're going through notes at home, you're looking through this PowerPoint, you can at least look at the example of like where does contrapositive fit in, and it's the negation of the converse. So you have to find the converse and negate it. All right. Now, logical equivalence. If you hadn't noticed when I did some of those examples up there, I said certain ones were true, certain ones were false. A logical equivalent is when you write sentences in different formats. Conditional, inverse, converse, or contrapositive. Certain sentences up there were actually the same sentence. They had truth values that were the same. So when you look at a sentence and you're like, oh, this sentence is true, or maybe they're both false, they share that same truth value. That's called a logical equivalent. So like sometimes, like in that case, the converse was true, and the inverse was true. That type of thing. But there's certain pairings. So for instance, typically a logical equivalent is the original conditional statement and the contrapositive. They usually mean the same thing. They're usually a logical equivalent. So like if the original sentence was false, the contrapositive is usually false as well. And we saw that with that last one. And the converse and the inverse usually have the same truth value. So the inverse would be true and the converse would be true. Those are called logical equivalents. You'll eventually start to see that they kind of usually share the same answers. I brought that up because some people notice that when you start doing a bunch of examples, like tomorrow we're going to do a bunch, and you're like, where they're always kind of coming up and being the same, like these two always match. That's just how they're supposed to work. Logical equivalence because of the way that the format works for if there's counterexamples or not. But again, they can both be false, they can both be true. It's just saying that they would share the same answer typically. Okay, questions on knowing which pairs kind of match usually. This doesn't say it just says their answers are usually the same. I'll let you write that down. Some people are still writing. Give you a little bit of time here. Check the cameras here. All right, questions, comments about the problems we've done? All right, perfect. Let's go to the next one here. Next example, I want to talk about conjunctions, disjunctions today. I talked about that last week when we did the logic grid for the problems with the Olympic athletes. I kind of warned you when you were reading through those problems, they used the word or and wrong. But I tried to explain it was a grammatical thing, they had to use it. Today we're going to really practice this concept of what and or mean. These are called compound sentences, when you have an and or in a problem. Sometimes people use them as run-on sentences in English. But for conjunction, it's using the word and, but in math, we use this little up arrow symbol. It's not meaning the power, it's not an exponent symbol like on a calculator, like up here. I know that the calculator does have that little exponent key, the little caret key. This is different. This is when you have two mathematical statements and you're saying the word and between them. They could even be sentences, and you're saying the word and between them. I think one of the examples I used last week, you're going to be served pizza and salad bar. If it uses the word and, both have to work. They both have to be on the tray because it said the word and. If they said or, pizza or salad, that's a disjunction, that's one or the other. Okay, so do we understand how the word and works? Both have to work, both have to be there. Okay, disjunctions, if you notice, they have a little down arrow symbol. Down arrow means disjunction, up arrows mean and. How I think of these symbols, by the way, this, like the conjunction, this kind of looks like an N that somebody wrote really poorly, versus this symbol, the disjunction, kind of looks like an R that somebody wrote really bad. Where you put the little tail on the R, where you write like something like this, and you just make it look really bad. Some people have really poor penmanship, where the R should have been like that, more or less. But just think of it kind of looks like a V, if you were to write poorly. That's how I always think of it. I know it's stupid, but that's just my little rule for how I think of like which symbol means which. So this means or, the disjunction. One or the other has to be true. If they said pizza or salad, and you went to lunch and they were only serving salad bar that day, they didn't lie to you. They said the word or, one was true and it's still true. So that really gets some people. So kind of think about that. They can do that for contractual things, so be careful like when you're signing for a new job. I know they do this a lot in car sales. If you're going to buy a new car, they say you have warranty for 100,000 miles or up to 4 years. That's or. So if 4 years comes around, you haven't hit 100,000 miles, your warranty's gone. Or maybe you hit 100,000 miles in 1 year. I don't know how you do that, but you hit 100,000 miles in 1 year. Then your warranty's canceled. That type of thing. They use the word or. One or the other comes first. Questions at all about disjunctions? Perfect. Okay, let's do an example of what I call a truth table. This is our first example today. This is my last problem of the day. We're stopping after this slide. This is my last slide. A truth table is where you try to figure out, is the overall sentence true or false? So what I mean by that, they usually give you, they can give you 3 or more different options. Sometimes they only give you 2, it just depends on what you have. We'll look at that here in a second. And so in my example, I give you a bunch of different topics. So I have P, Q, and R. Those are just 3 sentences that just made up 3 sentences in general. So a foot is 14 inches, September has 30 days, a plane is defined as 3 non-linear points. Some of those sentences can be true or false. I have no idea. So I just made up 3 sentences. So there you go, boom, boom, boom. My goal here is to figure out what is the possible truth table for this sentence. So I picked 2 of the sentences out. So I picked P and R. It's P or R, by the way. That's a little V, means or. And I want to know what are the possible outcomes that could happen here. So it's a part of like statistics. The probability of this being a true or false sentence. Okay? Now, this is the word or, correct? That's a little down arrow. So what does or mean in general?
One or the other.
One or the other. So if one of these is true, we're good. If they're both true, we're good. So we have a lot of options. I'm betting on, before we make this truth table, just by knowing the word or, knowing that little down arrow, the V, means or, that the probability of this thing being true is probably really, really high. Because of the word or, one or the other has to work. I haven't even read the sentences, I haven't even looked up to see if the sentences are true or false earlier. I'm just saying that just knowing the word or, this is probably a true sentence. Okay, so let's go through the truth table, and then we'll get to it. So I'm going to set this up, and then we're going to figure out these sentences are true or false to begin with. Okay? So here's how I like you to draw. I want you to draw a table with 3 columns going down. Now, why there's 3 columns you have to use the two letters that are here, P and R, they'll have their own column. So P will have a column, R will have a column. In the third column, it's the answer you're looking for. So it's the third column is P or R column. And if you want to put the word or, I'm totally fine with that. You don't have to use a little V symbol like I use. Okay, does that make sense how a truth table is going to be set up? P or R. Okay. Now, let's go through the math here. So what I mean by that is I'm going to write every possible outcome. I haven't even read these sentences yet, so I don't really mind. So I'm going to come back to the sentences earlier. These are all the possible outcomes that could have happened. They could both be true. So then your answer would be true. We'll get to that last. The first one could be true, the second one could be false. Or maybe the first one's false and the second one's true. These are the possible outcomes. Or they could both be false. Do you agree that those are like every possible outcome that could happen here? How I remember this, it goes true, true, false, false, true, false, true, false. So if you don't want to think of like every combination, it just, that's your setup. TT, FF, TF, TF. Some people just like to memorize that pattern. These are all the possible outcomes that could happen. I just think about a common sense. Now, the last column. This last column is made by looking at the front two. And you have to look at, this is the word or, correct? So like what Jacob said earlier, it's one or the other. So if one of them's true, my final answer is true. Okay? Because that's what or means. So, are one of these true? In the first, yes, so then the answer is true. Okay? Are one of these true?
Yes.
Yes, so then it's true. Are one of these true?
Yes.
Yes, so that would be a true. Are one of these true?
No.
No, so that would be a false. So what you're looking at in the last column is your probability of this sentence being true or false without even having to read the sentence in the first place, which is totally insane. I haven't even read to see if those sentences are true or false. I'm getting the probability of what's going to happen here. That's what a truth table is. Without even knowing the sentence, I can tell you by looking at this, my final answer here, that if you look at this, one out of 4 chances, because there's 3 trues and there's 1 false, 1 out of 4 chances this thing could be false. That's a really low percent. By the way, 1 out of 4 chances is 25%. 25% chance this sentence will be false. The original sentence, this thing. 75%, 3 out of 4, is telling me this sentence is probably going to be true. The original sentence, without me having to read the sentences yet. That's what probability is. I'm looking at how many outcomes there possibly was and what the logic is by just knowing the word or. Does that make sense, like what I'm doing here? We're gonna do a bunch of these tomorrow, by the way. All right, so let's go back and read the sentences, okay? Because I haven't even read the sentence. So let's look, and there's the word or in the middle here. That's the word or. Okay, let's read sentence number P, or letter P here. So let's look at that sentence. It is 1 foot 14 inches.
No.
Ugh, okay, this is false. Not good. Okay, so it's a false. So that means it's one of these two. One of those 2 possible outcomes. But the crazy part is, it's still 75% chance of being true. Even though I limited it down to 2, it's not 50-50 anymore. It's still 75%. I'm probably banking this is going to be a true sentence. Just because of what the original math was. It hasn't changed even though I've been eliminated. Okay, R. Okay, so the R here. Let's read that sentence next. So I'm going after this sentence. A plane is defined by 3 non-collinear points. Does it take 3 points not in a row to make a plane? Yes, that is the definition of a plane. So that is a true sentence. So this is what I have. Which row is that? Which row?
Third.
Third row. So my final answer is true. This is actually a true sentence. This is true. So you really have to kind of know your definitions and stuff. We're going to practice this more tomorrow. That's my last slide today. You're done for the day. Make sure in the next couple of days you bring your notes. We're probably looking at a test maybe middle of next week because we're almost done with the chapter. So maybe this week I'll give you your practice guide.